Welcome everyone. So let's wait for 5 more minutes to see if other people join. Then we will start. I think we can start now. So please confirm if you are able to see the screen and am I audible? Anyone? Am I audible? Okay, fine. Thank you. So yeah, let's start. So welcome. This is NOC24 EE-139 tutorial session on microelectronics devices to circuits. The course instructor is Professor Sudev Dasgupta from IIT Roorkee. I am Debashish Nandi from IIT Kanpur. So as you know, we go live every week, 3 to 5 p.m. Okay. So these are some of the prerequisites. I hope you guys have the YouTube playlist link now where the lectures are posted. So yeah, let's begin. So this is week 5. Okay. Let's start from where we left off last week. So it is asked that the conventional limit for subthreshold slope for MOSFET at 300 Kelvin is. So let us make a correction here. It is they are talking about the subthreshold swing. We'll get back to the thing that what are these. So what is subthreshold and all? Let us discuss first. So if I tell you that this is the gate voltage axis, say gate voltage, okay, and I mark you these 2 points. One is flat band voltage, another one is threshold voltage. So can you tell me what are the name of these regions? So this is called inversion, this is called accumulation, and what is the region in the middle? Can anyone tell me? This is threshold voltage, right? So what is the region in between accumulation and inversion? You can unmute and speak up. What I am asking is that what is this region? So this is called your, yeah, what is this region?
Sub-threshold region.
Okay, so first of all, this is called your depletion region. Okay, but yes, you are right that this also called your subthreshold region. So basically, what is happening is that anything beyond this line, below this point, means below your threshold voltage, is your subthreshold region. Subthreshold region. So the question is that uh, why are we focused about only this part, right? We are not focused about accumulation. So if I draw a MOSFET, let's say this is my N plus, this is my N plus, this is my P type substrate. Let's say this is ground, this is my VD. Yeah, 60 millivolt per decade is the right answer, but can you tell me why? And what is the significance of this value? Why we are looking for specifically the subthreshold region? So who has answered that? Shiva. Shiva, can you tell me what is the significance of subthreshold region? Why we are Worried about 60 millivolt per decade? I think there is some connection issue with Shiva. So yeah, continue. So let's take a cut line at this position, okay? And draw the band diagram of this. So a few points to note that if you see the band diagram, energy band diagram, you would see that something like this, okay? So basically this is your source, that is your N plus, this is your channel, that is your P type, and this is your drain, that is your N plus. So basically it is two N plus P junctions back to back, okay? I am drawing the band diagram along this line at this position, just at the interface. So you see that, and what we are concerned about, we are concerned about only EC. Why? Because the current mainly will be conducted by the electrons. You can draw the other bands also. For example, you can draw this will be your EF, then similarly something like this will be your EV, right? But we are concerned about only this line because electrons are basically what will be carrying the current. So let's say that electrons are residing at this place, okay? And you want the electron to travel from this place to this place. So what are the possibilities? That it has to go up this hill, okay? So what it is seeing? It is seeing an energy barrier. Fine. Now this energy you need to reduce to get more amount of electron to cross over to the other point. Because in a NMOS, what is happening? This is your grounded, this is, and B is also grounded, and you are applying certain voltage here. Let's say you are applying VD equal to VDD, some positive voltage. So what will happen? That your band diagram will something be like, if I just ignore this EF and EC and just focus on my, let's say, so this will be basically your VDD, QVDD, okay? So this is now your EC. Now what you are looking at is a energy band diagram where electron has to cross from source region to drain region. But at this place, at the source channel region, at this point, this yellow highlighted point, it is seeing a barrier, right? So electron will not be able to directly move to the channel. So what is happening? You are applying a gate voltage. Let's say you are applying a gate voltage greater than your VFB. So you are in your depletion region. So what will happen? This energy band diagram will be something like this. Okay. So this barrier is effectively getting reduced. So more and more number of electrons will start to cross the region. Fine. And now let us take a case. This blue case is when your VGS greater than your VTH or greater than equal to your VTH. Then what do we see? The barrier at the source end is almost vanished. So the barrier is here 0. Fine. So that is why most of the electron will start to conduct. And in the MOSFET diagram, what you see that there will be electrons here. So creating an your n plus kind of scenario where electron can move from this region. This is your source, this is your channel, this is your drain. So electron can move freely. Okay. So now what are the consequences of this in terms of transport or current conduction, right? So what kind of transports you have? You have I equal to, let's say, I drift and I diffusion. Fine. So what is your drift? Drift component is proportional to your q times n of x. Let's say this is the x direction, okay? And then your electric field at the x direction times your mobility, right? Electron mobility. This is your drift current component. And what is your diffusion current component? Proportional to your q times diffusion constant times your gradient of the carrier concentration along x direction. Okay. Now assume, think of this case, this green case. That is the case of depletion, or in other words, subthreshold. In accumulation, we are not worried about current conduction because I have a huge barrier. In accumulation case, what is happening? When your VG is less than VFB, your barrier will be further increased, right? This barrier will increase. This is the case when your VG is less than VFB. Okay. So almost no electron will pass through the channel because you are having a holes at this case when your VG is less than VFB. Fine. So now let us look at these two terms very carefully. In your subthreshold region, let me just add another page. So in your subthreshold region, what is happening? Your n of x, that is the channel electrons, are very less, right? Why very less? Because most of the negative charges will be contributed by the depletion charges in the p-type substrate. And that depletion charges do not conduct current, right? Because these are immobile charges. So your drift component, however, your electric field is same. Okay. Let's say if this is your L, so your electric field will be somewhat approximately your VDD over L, right? VDD minus 0, the voltage difference between drain and source over your length. So this remains same, but this is almost negligible. So what is happening? It is the product of this term and this term. So your I drift becomes almost equal to 0. Okay. So majority of the conduction in your subthreshold region is due to current conduction in subthreshold is dominated by I diffusion. Okay, please remember this. And how will I diffusion take place? Let's say, this is your oxide, okay, and these are the your N plus source and N plus drain. So you are applying certain gate voltage at this point. Let's say Vg equals to Vth plus some delta V, which is positive. Okay, means you are applying, or let's say not this. Let's say this is something V1, V1, and VFB less than V1. less than VTH. That means we are in the subthreshold region. Fine. Now here what we have? Here you have your VDD. Fine. Here what do you have? You have your zero voltage. So the concentration of electron at this point, N of x, will be more than the concentration of electrons at this place. Let's say this is n of source of x, and this is your n of d of x. And why I am telling that? VDD, let's say you're around 1.2 volt, and your, let's say, VTH is around zero point 0.4 volt, right? So less than 0 0.4 volt, let's say my V1 is around 0.3 volt. Okay. So what is the difference at this point between at drain end? Let's say this potential we call it VCH. Okay. At drain end, VG minus VCH drain is almost negative. Okay. Why? Because your VCH is your VDD 1.2 and this VG is your 0.3, right? Even electron may not be present at that point. Fine. But in this case, what is happening? In this case, your VCH is, in this case, your VCH is 0, but your VG is V1. So your VG minus VCH source is greater than 0 and approximately 0.3. So there will be electron. So electron at drain will be much greater than, electron at source will be much greater than electron of drain. So it sees a concentration gradient. Okay. That is what leading to my diffusion current. This leads to I diffusion to dominate. So this is the case of subthreshold. Okay. Now in case of this region or this blue curve, okay, or your inversion, what is your I diffusion? I diffusion is Q times N of x times epsilon of a current of x times mu of n, right? This has now large. This is now large. Why this is large? Because beyond your threshold voltage, you have a large number of electrons connecting between these two regions, right? First of all, from the band diagram, you can see that large number of electrons can pass over the barrier because there is absolutely no barrier almost, and you have a large number of electrons in this place that is creating this continuity. Okay. So now this is, we have epsilon s, again it will be around your VDD minus 0 over L, so it remains same. So this start to dominate over diffusion current. Okay. So moral of the story is, in case of inversion or when the transistor is on, the current transport is dictated by your drift component of the current. I will be your I drift. Okay. Now, how can you see it in the plots? If I plot your ID versus VG, so how does it look like? It look like this, right? Square law. and somewhere here you are having your VTH. So this portion of the region, seeing wrong symbol. This portion of the region is your inversion, and current is mainly drift, right? And this portion current is mainly diffusion. That is your subthreshold. Now it is not sufficient to look at only linear plot. Okay. So what we will do, we'll plot Vg at this point and we'll plot log 10 of ID. So how will this plot look like? This will look like something like this. Okay. So around this point, you will have your VTH. Somewhere here, you will have your VFB. Okay. Now let me mark. So this is your basically subthreshold region, and this is your inversion region. Okay. So now let me mark some of the key points. So this is your on current. This current, when your Vg is 0, is basically your off current. Okay. So can you tell me, in any case, will your off current be 0? And if not, then why? And if yes, then also why? The question is, can Ioff be 0? In this case, your transistor is on, and in this region, your transistor is off. VTH is the point. So can anyone tell me that what is the significance of off current? Means, do we want it higher or lower? So question is, do we want ion higher or lower? Another question is, do we want Ioff higher or lower? And if we want that, why do we want that?
So we want lower because when we
Lower
off the
what? Ion?
eye off,
Okay. So let me just write down. Ioff we want lower, right? Why do we want that?
when we switch off, um, uh, margin will be greater if that is lower.
Means what is switching off? Switching off means you are putting your VG to 0, right?
Yes,
That means you are just plugging out your power supply.
yes,
Then what do you expect? How much current there should be?
zero.
But what will happen if current is not 0?
Zero reads as one.
No, no. Suppose you have a mobile phone, right?
Yeah,
You have charged it. Let's say you have charged it to 100%. Okay.
okay.
Now you are not using the mobile phone. Okay. That means you are not turning on any of the transistors. Now what do you want your battery life to be? It should last infinitely. It will
Yes.
never get discharged.
Yes.
But as soon as eh, you keep the mobile phone in a standby mode or whatever, in a let's say you do not operate anything on your mobile phone, but you keep it as it is, just in idle condition. So you will see that after 7 or 8 days, your mobile phone battery will get drained. So where that draining is happening from? That is due to this off current. Okay, means even when you switch off your transistors, there is a certain amount of current flowing. That is certain amount of current leaking. So this off current we call as leakage current, right? Leads to leakage power dissipation. Leaks power at standby mode, right? So this is we do not want. So we want our Ioff to be as low as possible. And this is happening because of what? This is happening because of your VFB is negative in a PMOS. So that is leading to this non-zero current in this region. Okay. So your subthreshold region is expanding. Subthreshold region is expanding your across zero voltage. Fine. So we want our Ioff to be lower. Because we want to reduce our leakage or standby power dissipation. Okay. So that the battery lasts longer. But what about ion? Do we want ion higher or lower? What do you think?
So higher than
Why?
I of. So because
So
of
ion, no, I am not talking about with respect to I off. I am talking about, let's say I am giving you two options, 1 milliampere of ion and 2 million or 2 milliampere of ion. What will you choose and why?
so 1 million. So
You want lesser ion.
so because there might be a chance of thermal runaway because the
No,
IC.
let's say thermal runaway is at 5 milliampere. That is out of your region. Within limit, I am giving you two options. So do you want higher ion or lower ion?
Higher than higher.
Why?
So because we might be needing a minimum amount of current so that the transistors can turn on and
No, actually, it is not that. This is not the reason. We want higher ion.
Resistance. Higher ion means more number of charge carrier, which can lead to low resistance of my device.
Okay, one case is your low resistance. We'll come back to that. But what is the main purpose is your speed of device is proportional to your ion. How? Let's say tau is your delay, right? Tau is your delay. That means it is the inversion charge built up versus your ion. Okay. So if your ion is higher, so your delay will be lesser. So speed of the circuit will increase. As Partsathi has rightly pointed out that it is indirectly or directly dependent on your Ron. Okay. When we will discuss switch today, how the inverter in the inverter and the switch model, then we will come back to this point and explain that how higher ion helps you to achieve lower delay. numerically we will see, okay? But for the time being, you understand it in this way, that your time is charge divided by current. So thus more speedily you will build up your charge or the inversion charge, the better for your speed of the device. So that means you need your higher ion to reduce tau. That will increase the speed of your device. Now, so I have two scenarios, okay? So we want ion to increase and let's say Ioff to decrease. But for as who is that Jaideep has pointed out that it is not always possible to increase your ion because of various factors. Your on-state dissipation, power dissipation will increase. Okay, then your W by L ratio may not be that much sufficient to increase further to increase your ion. Mainly the limiting factor is your power dissipation or the heating issues. Okay, so let's say ion is my fixed. But then also I need to reduce my Ioff. So from this diagram, let me just copy it. So can you tell me how is that possible? Means what do I need to change to get same amount of ion? So I want this ion, but I want a lower Ioff. Let's say I want this Ioff. So basically the curve which will follow is something like this, right? I need to design my transistor in a way such that my IV characteristics follow this kind of plot or this kind trace back to this kind of IV curve. Okay. So now can you tell me what is changing basically between the black line and the pink line? So this is the change what we require, right? So slope of your log ID versus VG has to improve or has to increase, right? To achieve this condition. Do you agree till this point? If not, I will explain again. Confirm anyone that you have understood till this point.
Yes, sir.
So we need to go
Yes, I
from
got
the
it.
black curve to the pink curve. Okay. So that is our agenda. Because I want my, and you also might have heard in your previous courses that we want a higher ion by Ioff ratio, right? The reason everything is mentioned here, that why do you want your higher ion of over Ioff ratio is the same thing, because we want my Ioff lesser, ion higher. Okay. So now the slope of the log ID versus VG curve I need to improve. So let me, I should define this slope, right? So this slope is basically your sub-threshold slope or S. That is defined as, how do you define a slope? Dy by dx, right? So what is my y here? My y here is log of id, because I am plotting it in log scale. And what is my x? X is my dvg. Okay. So this is the definition of subthreshold slope. And the unit, always remember, it is expressed in volt inverse. Okay. There is another parameter that is called your sub-threshold swing, and that is nothing but 1 over S. Okay, and that is, by the way, this symbol is, what is this symbol? Can anyone tell me? You should know this. This is called defined as. Okay, when I am defining something, or when I am writing some equation by definition, so I will use this symbol. Okay, so 1 over S is what? dVg over d, or you can now d same thing, because there will be other parameters also on which your id will depend on, id will depend, right? So to be consistent, let me just use d, so log 10 of id. Okay, so the unit of this is millivolt per decade. So decade has nothing, no unit, it is just a connotation that log 10 is what? If you increase your id by 10 orders, then your log of that will increase by 1 order, right? Log 10 is, let's say, your I2 by I1. So if this ratio is, you increase I2 by 10 orders, so this will increase by, this entire stuff will increase by 1 order. So this is called per decade. So if you see the axis readings, it will be like something 10 to the power minus 12, 10 to the power minus 11, 10 to the power minus 10, 10 to the power minus 9, in this form. Okay, this is how your log axis looks like with units or scale. So can you tell me, from this line, my S and SS, should I increase my S or decrease my S? From these definitions and this line, that slope of id log this has to improve. So can you tell me what is the desired? So S should decrease or S should increase? Anyone?
So this sub-threshold slope should increase so that we could get
Right.
lower Ioff.
So your subthreshold slope should increase, right? And what about SS? Obviously SS should decrease because it is just inverse, right? So this you have to understand that why this is required. Fine. Now I will just write one equation of your SS. So if you derive your SS, it will come out to be natural logarithm of 10 times kt over q times 1 plus C depletion over C ox. Okay, what is your C depletion? C depletion is your epsilon silicon over W depletion. And what is your W depletion? W depletion, you know that it is nothing but 2 epsilon silicon times your surface potential over Q times your doping. And what is C ox? Is epsilon ox over T ox. Okay, so this equation, how this came about, is not in the scope of this lecture or in this course, but detailed derivation you can do. It is pretty easy. I will just point out the steps. What you need to do, you need to start with your current equation and assume that I subthreshold is basically I diffusion, right? And what is that? Diffusion will be your Q times what? Q times D of N times D of N of X times dx. So you take your dn and d qnx times dx. that is your dn times q inversion charge over dx. You express your q inversion charge as a function of. So can you tell me what just come into your mind immediately, that what will your q inversion be a function of which voltage? Is it the function of gate voltage or the function of drain voltage? Q inversion is a function of your gate voltage, right? Because it is the field effect, the vertical dimension, because your gate is positive, that is what pulling out the electrons at the interface. So this is basically a function of VFG. So if you just do this derivation and use the SS definition, so you will get back to this equation. Let's say this is equation A. Okay. So it is no rocket science. You can do it easily. For example, if you need any reference for this proof, you can look at Simon Z's book. Okay. So enough said. So let us just look into this equation carefully. So this was my subthreshold swing, right? So what do I want this to be SS? I want SS to be as minimum as possible, right? So can you tell me what is in control of you to reduce SS? You have what? This is a constant term. This is a constant term. This is your thermal voltage. That is also a constant. One is also a constant. So you have a C
C
depletion
depletion.
over C ox, right? So you can play with C depletion over C ox term. So you want to reduce this term, right? So that your SS gets reduced. So for us, let's say, what is the minimum possible value of this term? Can this be negative? The ratio of capacitances, can this be negative? This cannot be negative, right? This is the ratio of capacitances. So what is the possible minimum value? So the possible minimum value is 0. Fine. So what is your SS minimum? SS minimum is your natural log of 10 times KT over Q. So that is your natural log of 10 times 26 millivolt per decade. So if you do that, it will come out to be 60 millivolt per decade. Okay. So this is the minimum possible value of subthreshold swing. Fine. And how do you calculate your subthreshold slope? It is nothing but your S max is 1 over SS min. Okay. So what is the significance of this? Significance of this is, let's say you have a VG and log 10 of ID plot. Let's say this is your characteristics which your device shows. Now, by optimizing this ratio, you can get minimum 0 volt. That means, let's say you can get minimum of this value. Let's say here your inverse slope, that is 1 over S. SS is 60 millivolt per decade. So physically, if your T is not equal to 0 Kelvin, then there will always be a non-zero off current. Okay, that is the significance of this. Now, in this equation, if you put T equal to 0, that means your SS min can be 0. SS min 0 means this is your slope, right? Just the direct fall. Okay. So in this case, your SS is almost equal to 0. That is, let's say your temperature, let's say in your 10 millikelvin kind of range, or T very small. And this happens, by the way, if you reduce your temperature, operate your MOSFET in a temperature that is around your, let's say, liquid helium or 4.2 Kelvin or below that, those temperatures are available. You heard about quantum computers, right? Those kind of computers operate on this kind of temperature range, 10 millikelvin, 100 millikelvin. Okay, so these are called your cryogenic temperatures. So there it is possible, but what we are talking about is that at room temperature, when you use your mobile phone, so no matter what, as your T is thermal voltage is not, temperature is not equal to 0 Kelvin, that means there will be a certain amount of leakage current. That means if you charge your mobile phone, put it aside, be sure that after some time it will get discharged. You cannot do anything about that. But we want to delay that as much as possible. And if we want to get the maximum benefit out of it at room temperature, what my subthreshold slope should be? It should be 60 millivolt per decade. That is the lowest minimum possible. So is it now clear that why we discuss about subthreshold swing slope, and this is called, by the way, this limit is called Boltzmann's limit, or someone, it's called also Boltzmann tyranny also, right? So this is the idea behind the thing of this entire discussion. Okay, so please tell me what part you have not understood. I'll repeat again, otherwise I'll move on, because this is a very important concept. Even in any job interview or any higher education, if you want to go, this kind of question will be asked, that why subthreshold slope is important, what is your Boltzmann's limit, what if the temperature, I reduce the temperature, will the Boltzmann's limit still be 60 millivolt per decade? I think you are now will be able to answer all these questions after these discussions. So are you comfortable with this discussion?
Yes, sir.
So, okay, I assume that you have understood what I have discussed. Okay, so let's move on. Consider a N-channel N MOSFET as shown in figure below. What will be the change in ID if VDD changes from 3.3 to 1.8 volt? Assume this. Okay, so what I see that my VTH is 0.5 volt. Okay, first I note this. What is my VGS? VGS is the difference of these two. That is my 2.5 volt. So what is my V overdrive? VGS minus VTH. That is 2 volt. Now I see that my VDD is ranging from 3.3 to VDD is ranging from 1.8. So it is swinging from this to this. Okay. That means my VDD swings from this to this. What does that mean? What is this region of operation? And what is this region of operation? In one case, your VDD is greater than your VGS minus VTH. That is we called as saturation region of operation. And this part we will call it linear region of operation, right? So what do I mean by that? If I have a VDS and let's say IDS, I get this kind of characteristics, right? So let's say somewhere here, this point we call it VDS sat. That is on the first order, it is equal to VGS minus VTH. And in our case, it is 2 volt. Fine. And where the currents are, we are asked to calculate at this point, this is 1.8 volt. And at this point, this is your 3.3 volt. But what we see that this region where my 1.8 volt is there, it will give me a, let's say I2, okay, and this value will give me a current of I1. So this green region is basically your saturation region, right? And this yellow region is basically your triode or linear region. Okay. So why do I need to understand this? Because I need to use two different kinds of equations to compute my IDVD. Okay. In case of VDD equal to 3.3 volt, I will use ID saturation equation, that is half mu n C ox W over L VGS minus VTH whole square. Fine. And what is that? This is my half. This is 100 microampere per volt square. 100 into 10 raised to minus 6. And VGS minus VTH is a fixed value, 2 volt. So that is 4. Okay. Ampere. So what will it be? 200 microampere. Okay. Now, in case of this is your I1. In case of VDD equal to 1.8 volt, I have my I2 is equal to ID linear. So what is the linear equation? Mu n C ox W over, can you tell? W over L, then VGS minus VTH times VDS minus VDS square over 2. Fine. So this is my 100 into 10 raised to minus 6. And this is what? 2 times 3.3 minus 3.3 square over 2 ampere. So if you compute, it will come out to be 198 microampere. Okay. So basically, what is this value? 198 microampere. This value is 200 microampere. Okay. So they want us to find out this difference. Okay. So your delta ID will be I1 minus I2 mod of that is equal to 2 microampere. Okay, I think this is pretty straightforward, just using of the formula, but I assume that you understand Where does these formulas have came from? You know, right? How does these formulas come from? You know, right? This should be, noted to your heart. These two formulas. You should never forget this. I'm not sure if you guys are following or not. Okay, just let me ask one question. I think it will get through. How to go from this formula to this formula?
Current is not changing with VDS.
So you are right. Go on.
So ignore VDS.
Hmm?
How much when we increase VDS, no increment in current when it came to I
Right.
reset.
So that means you find out at which point this becomes zero, right?
Yeah,
And that will give you your VDS sat equal to VGS minus VTH, right? And then you just put your VDS minus VTH. So you have what? VGS minus VTH square minus VGS minus VTH square by 2. So it will be half VGS minus VTH square. So this half we take outside and this is the VGS minus VTH square. Okay. Okay. So let's move on. Okay. In order to have zero substrate bias effect, the substrate of an p-channel enhancement mode MOSFET should be. So first, let me ask you what is substrate or body bias effect? What do you understand of this? Please tell me. Meanwhile, while I am drawing the diagram. P-channel enhancement we will discuss later. Let us start with our discussion with the N-channel MOSFET. This is your VB. This is your VG. This is VS. This is VD. So can you tell me what is substrate effect? Means what is the common mode of operation when we discussed our other kind of NMOS structure? What did we do? We applied a bias here grounded, this grounded. We applied here VDD or some drain voltage, and we applied here, keep changing my VG, right? So the reference point or the reference voltage of the substrate was these 2 points was shorted. So normally source and body or substrate are shorted. Fine. In normal mode of operation. What if Vs is not equal to Vb? That leads me to body bias or substrate bias effect. Now to understand this effect, What I'll do, I'll just discuss it in a different way. I will take this structure, this much of the structure, and discuss on that. Then you will see that it is a very easy connotation to extrapolate the effect of body voltage on the entire characteristics. So if I just draw this, I have what? I have a MOS structure. So this is gate, this is body, this is N plus region, this is P, and let's call it some contact, okay? C. It may be source, it may be drain. Let us call it a C, okay? So how do you think the depletion region and inversion region will look like? So first thing is that let me just mark the inversion region. So this is your, let's say this is your inversion region, okay? And around this is your depletion region. So this is my VB. Let's say VB is grounded. So, and this is my VGB and this is my VCB. Okay. Earlier, what I was doing, I was just shorting these two and grounding, right? Now, what I am doing, I am applying a potential difference between the collector and the base voltage and the and the body terminal. Okay, the contact and the body terminal. So now, can you see that there is a PN junction diode forming here? You can see, right? There is a PN junction diode forming here. So whenever your VCB is greater than 0, just give me a minute. Yeah. So this is a PN junction diode, right? So you have a PN junction diode and you have a MOS device sitting together. So now if you note this very carefully, you can see two regions of operation. Let me just bifurcate this. Okay. So this portion of the region, this part is your MOS structure, the MOS capacitor we had discussed in previous classes, and this is your PN junction. Fine. And there is a intermediate region. There both of the thing will get both of the thing will contribute to a little bit more. So now you let me again take a cut section at this point and draw band diagram. Okay. So this is basically your N plus region and this is your P type channel, right? A P type substrate. So if I draw the band diagram, how will it look like? It will look something like this, right? This is your EC, let's say. When your VGB is equal to VFB, then can you tell me what is the value of this barrier and your VCB equal to 0? So the question is basically you have a PN junction, N plus P junction. This is your C, this is your B. So you have a both of them are shorted. So you are drawing the band diagram like this. So what is this value? What is this voltage? Anyone? In a PN junction diode, if your both terminals are shorted together, that means it is in equilibrium, no current is flowing. It is equivalent to having these two terminal open. Nothing is connected to this. Then what is the potential across this region? What is this drop? This is your EC, right? This is your EF, this is your EV, this is your EC. So what is this value? Come on, guys, anyone? You can try, it may be wrong. There is no harm in that. Any one of you can unmute and assist me. In a PN junction diode, at equilibrium, if nothing is connected or both of the terminals, potential difference between both of the terminals at 0, then what is the potential that is generated around the depletion region? What does it call?
Intrinsic semiconductor, like EI.
Intrinsic semiconductor. No, you have heard of this thing, right? VBI, built-in potential. Built-in potential. Have you heard of?
No, sir.
You have not heard of built-in potential. Let's say you have read about PN junctions, right? Can,
Yes, sir.
can you please remain unmuted? So let me just please remain unmuted.
Yes, sir.
Okay. So this is your N plus P, right? So what will happen? Some depletion region will form. You know this
Hmm.
much.
Yes, sir.
So this will be your positive or donor atoms. This will be your negative or acceptor atoms, acceptor
Yes.
ions.
Yes, sir.
So now, if you draw the charge diagram or row, so what do you see? You see that you have a positive charge here and you have a negative charge here, right? This is what? This is your QND. Let's say this is the doping is ND, here the doping is Na. So this is your positive and this is your negative. And this will be your, what will this value be? Minus Q Na, right?
Yes, sir.
You know this much. this is xp, this is xn, and we have a relation that nd times xn has to be equal to xp times na, right? Because the both the charges have to balance.
Hmm.
This much you know, full
Yes,
depletion
sir.
approximation.
Yes, sir.
So now this is your rho, right? From rho to electric field, how do you plot? What is the relation from rho to electric field? Your d electric field of x over dx is your rho over epsilon, rho of x over epsilon. This is called Gauss's law. So from that you do what? You plot your electric field, right? So what your electric field will be? Electric field will be nothing but the integration of this plot. So it will be nothing but your this. This is how your electric field will look like. This will be your xn and this will be your xp. This much is fine.
Yes, sir.
And now from electric field, how do you plot your potential? This all are x-axis. So how do you plot your potential? What is the relation? Your d phi x over dx is equal to minus d phi x of dx is equal to electric field. This is the potential relation. This we have discussed in last class also, right?
Yes, sir.
So if you know your electric field, then you just need to integrate that and invert the sign, right? That means what? If I just draw this and this boundaries, so it will be something like this. So this will be this linear thing will become square, some quadratic thing, right? So this will be your potential profile phi of x, and what is this difference? This we called as built-in potential, right? VBI. And what is your, how will your energy band diagram look like? Just the opposite of your potential. That means your energy band diagram will look like this. This is what I have drawn. If this is your EC, everything will follow, EV will follow. And as it is in equilibrium, so this will be your, so this will be your EF. So EF will be constant as I have applied no potential, or I have connected both the, someone wants to join the call. So you got it right. How do I draw the band diagram and how I am telling that this is QVBI or the built-in potential? This built-in potential you can find out as phi t ln times NAND over NI square, right? I think this you have already done in your undergrad or first year. Even in first year they teach these things, right? So if you have not done this earlier, so I will suggest that please go back to any of the basic books like Streetman Banerjee or your Donald Nieman, okay, yeah, or Robert Pirret. You go back to those books and just read these things. These things you should not forget, right? That what are the potentials and what are the energy band diagram of an PN junctions? How does it look like? What are the built-in potentials? Okay, so then it will be very difficult for you to understand the advanced devices like BJTs and MOSFETs. Okay. So no harm. You just go back and check it again and then come back to this lecture and look. Okay. I think you will be able to understand it.
Yes, sir. Yes, sir.
So in MOSFET case, what I was telling that this N plus contact and this is P type substrate, right? So I was drawing the band diagram of this diode, and this was my oxide. Fine. So this will be how the Venn diagram along this x and x dash, this is x and x dash cut section will look like. Now you see when your VCB is 0, the potential barrier the carrier sees is your built-in potential. Fine. This built-in potential times Q. This built-in potential is nothing but it is coming from this analysis. Okay. Now what you have to do, is, okay, just let me redraw this part. Okay. So what is happening as you are increasing your VGB, so this barrier is starting to come down. Okay. And let's say at VTH, we know that this barrier almost vanishes. So this difference is your, the surface potential becomes 2 phi f at this location. Miraculously, this is almost equal to your VBI. Okay. So that means, how do I put it into words? This shift is your field effect. Okay. Two things to remember very carefully. What I am drawing is that I am drawing energy band diagram along this cut section. Vertical, but not vertical, but horizontal cut section. Okay. This barrier reduction is due to field effect. When I am applying positive voltage at the gate, my electronic energy will come down. So that is what is happening. And at Vg equal to Vth, my surface potential becomes 2 phi f. That means this diagram, the surface or the substrate surface energy comes down by a value of 2 phi f. That 2 phi f value almost matches your VBI. That is what is eliminating your this barrier difference. In this case, barrier is 0, right? So that's how a continuum of electron channel and n-type contact takes place in the first place. Now think your VCB is not equal to 0 and you are increasing your VCB. What will happen? This will also start to come down. So in this case, let's say,
सर
yeah,
सर जीरो कैसे हुआ?
which one is 0?
Uh,
At VGS equal to VTH, how it is 0, the barrier?
yes,
Okay. You had this, right?
yes,
Let's say this is your EC. So this was your N plus contact, or let's say for example source. And this is your P type substrate. At which location? At the surface. Now you are increasing your VG. This you have kept constant, right? This you have kept constant, this VC. Now you are increasing your VG. When you increase your VG, what will happen? First thing is your depletion will take place. Then electron will start to come at the surface. So what is happening to the band diagram? This value is getting lower.
yes,
Do
sir.
you do
Lower.
you see
N
do you
increases, a gap will.
do you see that much that with VG increases this will start to reduce?
Yes, reduce.
Okay. Now let me tell you numerically that what is your VBI? VBI is, let's say, your phi t ln NAND over Ni square, right? So phi t, let's say 26 millivolt. Ln is your Na and Nd, let's say Na is this substrate is your 10 to the power 17 and Nd is your 10 to the power 19 over 1.5 into 10 to the power 10 whole square. Okay. If you compute this, it will come around 0.8 to 0.9 volt. Okay.
Okay.
That much is clear. Now, when your VGS equals to VTH, this is the structure, right? This is your oxide. This is your B. This is your gate. So this entire VGB, this entire VGB falls into which two potentials? It will fall into your psi ox. Across oxide, some potential will fall, and
Some will fall
some
on
will fall
depletion,
on the depletion region, right? So your
right?
psi ox and psi s. So your VGB will be equal to psi ox plus psi s. Let's say flat band voltage is equal to 0. Assume your VFB is equal to 0. Okay, means the contact potential and all is 0. Fine. Now, when I am drawing this voltage, this line, so what is this potential corresponding to? This potential is corresponding to my psi s. Can you see that?
Uh, yes, sir.
Because I am plotting at this surface, right?
Uh,
So now, when VGS equal to VTH, what is your psi s? It is 2 phi f.
yes, sir. 2 5 F.
Clear?
Clear.
So now let's take what is your phi f? Phi t ln times Na over Ni. You just put 26 millivolt times ln. Just this becoming, so you have your psi s equal to 2 times phi t times ln Na over Ni. So what is your 2 what is your, this is 26 millivolt times ln over Na is what? Na we have taken 10 to the power 17, right? And this is 1.5 into 10 to the power 10. If you compute this, no, it will be your around zero point 0.8 to zero point 0.9 volt. So this value and this value are matching. That means the initial barrier you had, when your 2 phi f, this line will get pushed to this value. So the barrier at the source and surface interface will almost be equal to 0.
सर
Yeah,
सर मैथमेटिकली सर ठीक है, लेकिन
okay,
फिजिकली सर ऐसा लग रहा है जैसे कि वो भी एन है, ये भी एन है, मतलब जैसे चैनल बनता था ना, तो
okay,
टोटली इन्वर्जन होता था
fine.
पी सबस्ट्रेट में एन टाइप का। उसी तरह से ये पी एन जो है वो कंप्लीट एन जैसा लग रहा है, मतलब हमें ऐसा दिख रहा है पी
Exactly,
एन।
that is happening, right? The channel will get formed. Okay,
यस
this is your n plus, this is your p, right? This is what we are
यस
discussing about. So when your Vg will be equal to Vth, so what will happen? There will be already depletion charges, there will be, but
यस
at this region, electrons will also be present, right? So
यस सर,
this becomes a continuum.
यस सर, like that only in this way channel is also
Exactly,
forming.
exactly like that only. In this way, the channel is also forming. Now, why I discussed this much? Because now what is happening, the critical difference between the previous discussion and now is that your VCB is not zero anymore, right? So that means if you just copy this band diagram, so What happens when you increase your VCB? What will happen to this level? This will also drop.
Yes, sir.
So now think it in this way, that your VG is at VTH. Okay, let's call it VTH 0. Then your channel was perfectly formed, right? Now you have increased your VCB greater than 0. So what you are doing, essentially you are pulling the conduction band of the contact to a lower value. This value is nothing but your QVCB. So you are again creating a barrier, right?
Yes, sir.
So now to reduce this barrier, what do you need to do?
Uh,
You need
Decrease
to
the
push.
voltage.
No, you let us say that this is fixed. This is fixed. But you need to reduce the barrier. You want to restore the same level of inversion. What you can do?
Uh, Increase the doping, but it is
No, you
already
have
doped.
you have an easier control, right? See, this barrier reduction how can happen? Either you increase this thing or you push this thing down, right? I am telling that this is fixed by your VCB. So you need to pull pull your barrier down to this level. So how do you pull your barrier down to this level? You want your conduction band to come to this place. So how do you do that? In the in the interface or in the surface? How are you pulling the conduction band lower? In earlier case, how were you pulling down the conduction band in the interface?
By VG,
By increasing VG, right?
right?
So in this case, your VG has to be increased much beyond than your VTH 0 to get inversion.
Yes, sir.
So your as soon as you are increasing your VCB, what it is doing, it is increasing the barrier again. So to reduce that barrier, what you need to do, you need to pull your VGB further, right? You increase
Right.
your VGB further. But now can you tell me, if we increase VCB by delta VCB, so how will be my delta VGB? Will it be higher than delta VCB, equal to delta VCB, or less than delta VCB? Do you understand the question? The question is, let's say my VC was earlier 0 volt. Now I have make my VC equal to 1 volt, and my VG was earlier 2 volt. So what will now my VG be?
VGB 2.5 volt.
Why 2.5 volt? Okay,
To
just let me write down. Uh, at the onset of inversion, when VCB is equal to 0, VGB is equal to VTH 0. Fine. When VCB is equal to V1, VGB will be what? This is the question. So can you tell?
Sir, when we decrease the VTH, the barrier will be increased.
No, no. Why? How are you decreasing the VTH threshold voltage? I
VTH,
am
VGB, VGB.
VGB. We are increasing, right? We are not decreasing. We are increasing. Then
When
only
we
my
are,
barrier will decrease.
yes, sir. But you have to increase the barrier in below the conduction band. Sir, you ask a question once again. I didn't.
Okay. My question is that when my VCB is equal to 0, when my VCB is equal to 0, okay, let us put it in this way. This is source, this is channel, or this is surface. This is my EC, okay? So when my VCB is 0, there is no barrier, right?
Yes, sir.
This is EC, fine. Now, when my VCB is V1, I have a barrier. This is my EC now. This is at VCB equal to 0. This is at VCB equal to V1. My question is, how much gate voltage I need to apply to bring down this EC to this point to this point? How much VGB I need to increase? How much VGB? What is the value?
So same value.
Are you
VCB.
sure? That
Sir,
is the
looks
catch
like that
basically.
only.
Because when you increase, what is your VGB? VGB is equal to your VAB plus psi ox plus psi s, right? So what is your delta VGB? Your VAB is constant, so it will be 0 plus delta psi ox plus delta psi s, right?
Psi is also constant.
Psi s,
Sir,
why psi s is constant?
surface potential.
This is the surface potential, right? This is the energy equivalent to surface potential.
Yes, sir.
So this is not constant.
Not constant. Yes, sir.
So the matter of the fact is your surface potential has to be increased by V1. This is your surface potential, right? This potential has to be increased by your QV1 so that
Yes,
this
sir.
barrier is not present. So that means what? Your delta VGB has to be delta psi ox plus V1. This quantity will be additional. So what I mean to say is that suppose your VCB is 0, then let's say your VTH is 0.3 volt. Okay. When your VCB is let's say 1 volt, your VGB will be greater than 1.3 volt because your surface potential has to increase by 1 volt. But your overall VGB has to be increased by more than that. Why? Because your oxide drop is also present. Is it okay?
Yes, sir.
So your VTH new is now what? Your VAB plus What was your earlier 2 phi f? By the way, what was your VTH 0 plus gamma root over 2 phi f, right? This was your old threshold voltage equation. Now your VTH has become VFB plus 2 phi f plus VCB plus gamma root over 2 phi f plus VCB. Okay, so now this is with respect to VGB. If you take VGS, then this VCB you need to minus, right? Because your contact with, or let's say VGB and let's say VGC. Then VGC is nothing but your VGB minus VCB. Okay. So if you just take VTH with respect to VGC parlance, it will be VFB plus 2 phi f plus gamma root over 2 phi f plus VCB. Okay. So what is your threshold shift due to body effect? Is your VTH minus VTH 0. That is your this term minus this term. So it will be nothing but gamma root over 2 phi f plus VCB minus root over 2 phi f. Okay. So this is the manifestation of body effect. That body effect increases your threshold voltage, or the amount of gate voltage required to get a certain level of inversion. If you apply your body potential, then that gate voltage, a more amount of gate voltage will be required for you to achieve that same level of inversion. And how do I say that? This is explained in this diagram. That when you are increasing your VGB, that means you are reducing the energy barrier between the source and the channel. Now when your source is increased, then again the barrier starts to increase. To compensate that barrier, you need to increase your VGB further, but that value has to be more than the increase in the source voltage or the contact voltage. Okay, so this is your substrate or body bias effect.
सर
Yeah,
सर इन लीनियर मोड एनालॉग में जो हम लोग पढ़ते हैं वी डी एस शुड बी ग्रेटर देन वी जी माइनस वी टी
in linear mode, no, it is in
in
saturation mode.
saturation flat band
Yeah,
in flat band saturation mode
flat band saturation.
मतलब फ्लैट जिसमें रहता है सैचुरेशन मोड
That is not flat band. That band is energy, you
saturation
know. Saturation, yes, yes, okay.
saturation mode in saturation mode VDS is greater than VG minus VT
Yes.
so so can we increase much VG VG should be limited na
Why so?
मतलब
If you see, this is the plot, right? You are talking about.
yes which
What
plot
what will happen if you increase your VG? It will follow a different path.
uh,
It will not increase in this direction, but will increase in this direction, right?
yes sir.
So your ID is effectively increasing.
सर एक और क्वेश्चन था मतलब नॉनसेंस
Yes.
वाला क्वेश्चन लगेगा लेकिन जैसे आप
It
अभी
it doesn't matter. Shoot.
सर जो पाईऑक्स हुआ जैसे हम लोग सर्किट में बनाते हैं तो इंसुलेटर को ओपन सर्किट में दिखाते हैं और वोल्टेज एंड ड्रॉप अक्रॉस मतलब सारा वोल्टेज ओपन सर्किट में ड्रॉप हो जाता है तो यहाँ पे पाईऑक्स में हम लोग क्यों मतलब वोल्टेज उस तरह से क्यों नहीं ड्रॉप होता है VGS is equal to VAB plus phi ox plus phi s हुआ, तो phi ox is insulator, so it would not act as open circuit.
No, wait. So this is an oxide, right? This is, let's say, SiO2. So this is your B, this is your G. So you are applying potential across these two terminals, right? Okay.
Okay.
Now you mean to say that, so what is open circuit?
Insulator.
No. Open circuit, what is the IV characteristics of an open circuit?
Parallel to सर आई भी लिखिएगा तो
Let's say, what is the I flowing through this?
0.
I is 0, right?
Yes sir.
So it will be this line.
Yes sir.
Okay. So voltage can be anything. So what your question was that, why don't the entire thing drop across this point? Why should it be? It can be anything, right? It can be this point, this point, this point, this point, this point. It will depend upon the boundary condition of other parameters. For my case, if there is another terminals, let's say this kind of terminals are charges are present. So my ground plane shifts to this. So there will be a two parallel plate capacitor. Now when you are talking about VGB is equal to VFB, then there is no charge in the semiconductor. That means there is nothing present in this case. So what is your only capacitance? Your only capacitance will be this, what the case you are talking about.
Okay.
When you see your capacitance voltage characteristics, you see, right, your CV is like this, then
Yes.
this, then this. This is what point? This is your VFB. So at VFB you will have what? At VFB you will have Cox only the front capacitance. And below that, what is happening? Your charges are plotting at this point. So open circuit has nothing to do with your potential drop. Because in open circuit, what is the main condition is that current is 0. That means my transfer characteristics or IV characteristics is this line. Voltage can be any value.
Okay. जैसे सर्किट में हम लोग जो करते हैं वो गलत करते हैं.
What do you do in circuit?
ओपन सर्किट में कंप्लीट वोल्टेज ड्रॉप, जैसे सेल है, रजिस्टर है, ओपन सर्किट है, तो 5 वोल्ट बैटरी को ओपन सर्किट के
Cell,
बाद 5 वोल्ट,
resistor, cell, resistor,
then open circuit, then
then open circuit.
across,
Okay.
yeah,
Yes.
across these two terminal 5 volt. This is due to I is equal to 0.
This is due to I equal to 0.
Yes sir.
Exactly. So what is
Yes.
the voltage here?
Yes
It
sir.
has to be 5 volt.
Yes sir.
I0, otherwise if you apply, this is, let's say, VB, this is your VA, and this is ground. Until unless this becomes same, how will there will be some current flowing through this resistor, right?
Yes sir.
So
Sir,
that
in
is nothing to do with this thing.
any circuit is possible where this 5 volt doesn't appear other than 5 volt in open circuit.
Other than 5 volt,
In open circuit condition, any kind of circuit.
you can charge a capacitor, right? Let's say you have some kind of source here, right? This is R, this is C. Let's say this is, you apply a pulse, a current will flow, and it will at your infinite time it will happen what? This is your step you are applying, right? How will the voltage across the capacitor will be? Let's say VO. VO will be something like this. So 5 volt will appear after some time. Let's say 10 tau, let's say, and tau is equal to your RC. May not be exactly 5 volt, but 4.9 and much beyond that.
Yes, sir. ठीक. Thank you.
Okay. Okay. So, yeah. So, what was the question that? So, moral of the story, your substrate effect, substrate bias effect or body bias effect will not be present if your VSB is equal to 0. Fine. Now, for a NMOS, my source is generally connected to ground and higher voltage is applied to the drain, right? But in case of PMOS, just the opposite happens. Source is connected to the high supply rail and my drain is connected to the ground. If you just see an inverter, you can easily check that. So this is your VDD, this is your ground, this is input, this is V output. Okay. So what is your source here? This is your source. This is gate, this is drain. In this case, this is drain, this is source, this is gate. Fine. So this is your PMOS. Your body will be connected to source. So what is that source? Source is connected to the supply rail or the highest potential. So to have zero substrate bias effect, your substrate terminal has to be connected to the most positive bias because my source is connected to the most positive bias. And to mitigate substrate effect, my source and body should be connected together. Okay. Or my VCB or my VSB should be equal to 0. You can also verify it using this equation. If this is 0, then this entire term becomes 0. So my delta VTH becomes 0. That means my body effect becomes 0. Okay. So moving on to the next thing is that calculate the threshold voltage of the MOSFET shown in the figure. Okay. So what do we see? We see it is an NMOS and the body terminal is connected to 1 volt. So we found out, right? My VTH is equal to VFB plus 2 phi f plus gamma root over 2 phi f plus VSB. Fine. So my delta VT is equal to what? Delta VT is equal to gamma root over, or I can write it in this way, VFB plus 2 phi f plus gamma root over 2 phi f plus gamma root over 2 phi f plus VSB minus gamma root over 2 phi f. Okay. So this is what? This is your VT0. Okay. So your VTH is equal to VT0 plus delta VT. So your gamma is given, 2 phi f is given, VT0 is given. Now you need to find out what? You need to find out your, for example, your ID is flowing 1 milliampere, right? So this ID will fall through this also. And this voltage is 200 ohms. So what is this voltage? 0.2 volt, right? So if it is 0.2 volt, then what is your VSB? VSB mod is your 0.8 volt. Okay. So now you know this is given, this you know, gamma you know, VT0 you know. So you can calculate your VTH. Okay, so do this as homework. So the main purpose of the discussion in the previous section was to compute this equation. Okay. Okay, it is given that mu p is equal to, so mu p is equal to 0.4 mu n. Okay, so by the way, can you tell me why the mobility of holes is always lower than the mobility of electrons? Can any one of you tell me that?
So due to mass,
Due to effective mass of the
electron,
hole is
electron
greater
higher.
than effective mass of the electron, right?
Yes, sir.
Because my mobility, we know that it is q tau over m star, right? It is inversely proportional to m star. Okay, good. And another thing is that, so I need to have idp, let's say half mu p wp by lp cox vsg minus vtp whole square, and idn is equal to half mu n wn by ln cox vgs minus vtn whole square. Okay, so what they have to operated in the saturation region, so we have used saturation region equations. Okay, overdrive voltage, these are my overdrive voltage, these are also same. That means this is same, cox is same, and my IDs are same. Okay, I need to find out the relation between WP by NP. Okay, and my LPs are also same, equal channel length. So what do I get? I get mu P times WP is equal to mu N times WN, equating these two equations. So mu P, so I want to find out WP by WN, so it will be equal to mu N by mu P. What is mu N by mu P? 2.5, right? So why this problem is important? This problem is important in your inverter sizing. Okay, when we will go to inverter sizing, we will see that you have this kind of scenario, right? This is your input, this is your output, and this is your VDD. So same current is flowing throughout, because in your silicon, what is your mu P? Mu P will be your around 500 centimeter square. What is the unit of mobility? Anyone? Quickly. Unit of mobility? I think you should be able to answer this. Anyone? Unit of mobility? Unit of mobility is centimeter square per volt second, right? And what is your mu n? Mu n will be your around 1000 centimeter square per volt second. You may say bulk mobility is 1350, but that is never achievable, because why the, by the way, it is also a very interesting question, that mu n Okay, this I will start next class. So mu n is equal to 1350 centimeter square per volt second in case of silicon bulk. But in case of MOSFETs, you get around mu n around 1000 centimeter square per volt second, even much below that also. So, what is the reason of reducing the mobility, mobility reduction in case of MOSFETs?
In MOSFET, electron have to move uh, through the surface, near the surface.
Okay, so electron has to move near to the surface.
Yes,
So, what do you mean by surface?
surface, oxide surface.
So, this is oxide, right? So, it is basically two material, SiO2, and it is silicon, right? So, this
Yes,
surface will have roughness. What do we mean by roughness? Roughness means there will be dangling bonds, right? Unfulfilled silicon bonds. Means there will be a region where it will be SiOx and X will lie from 0 to 2 and then it will have a SiO2. So when X is 0, that means it is simply silicon, this place. X is 2 is this place, but between there will be transition region and electron moves at this place only, near the very near to the surface. So it sees a lot of capturing locations or scattering locations. This we call as surface scattering. Last class I have mentioned briefly that there is one phenomenon of scattering, that is surface scattering. Due to this, the bulk mobility of silicon gets reduced for both holes and electrons also. Okay, but again, due to the difference of effective masses, the mobility of holes are almost half as that of electron. To compensate that, to have the same ID in this and this region, what we do, we just increase the W by L of the PMOS. Basically, your W by LP will be generally twice of Wn of Ln. So that this is multiplication, right? You can see from this example that by increasing the W of the PMOS, we can cater for same amount of current due to the difference in mobility. Okay, we could have done it with the length also, but why don't we do that length? Because length, we always want higher current, right? And reduction of length leads to many other effects. Short channel effects, if you have studied, those starts to appear. To avoid that, we keep L same and we just change the W. We keep my PMOS, the size of my PMOS is twice. Basically, what is happening? If you see the inverter, your PMOS will be like this and your NMOS will be like this. Okay, this is your NMOS, this is your PMOS. So this is your basically WP, this is your WN, and L remains same. So this will be how your inverter, if you take the footprint, it will look like. Okay, so yeah, I think a lot of in-depth discussion we had today. So let's close here. Next class I'll mainly focus on CMOS inverter and how to size them, how to compute the delays, and what are the aspects. Okay, yeah. So I think if you do not have any question, we can stop here. Okay, thank you everyone.